Not name, first name. Majid is Arabic.
Yes, Majid, because
But Taki is
we have
also.
Majid in Iran, and I thought
Yeah,
you are Iranian.
I
Ah,
know.
okay, okay.
Yeah.
Nice to meet you.
Okay, okay, we can wait a little bit. Thank you for the letter. It's a very nice letter, and it's already in the project. Like everything is okay.
Okay, so let's start. Today we have a seminar by Professor Majid Taki. Majid Taki is a full professor at the University of Lille and is head of the Nonlinear Dynamics and Optical and Biological Systems team at the PHLAM laboratory. Majid is an expert on nonlinear dynamics in optical systems, instabilities, and he has been working pattern formation, feedback effects, spatial turbulence, absolute and convective instabilities in extended systems, fiber lasers, dissipative solitons, rogue wave, and stochastic patterns. And today, one of the topics is rogue wave, the one that he's going to talk today. Besides that, Majid is a good friend of ours and has visited a long time ago, but we have been meeting him in some meetings and so on, Damia and myself, and we have been interacted many times. Majid has published over 70 papers in different journals and has been invited to more than 20 conferences, and he has been also responsible for several European and international projects. And very recently, he founded a new thing that has been created in France, which is a European Center for Mathematics, Physics, and Earth Interaction. And basically, it is composed of mathematicians and physicists, and it is hosted at Lille, and they aim at working on nonlinear science, which is pretty much close to the topics that we are doing here. Majid also has been a member of the National Committee for Physics Research of the CNRS, which basically is the part of the CNRS that oversees all the institutes in physics. So it is a pleasure for me to have Majid here, and please, thank you.
Okay. Thank you very well, Pera. I am really very happy to be here, and I would like to thank really the organizer for inviting me to this nice summer school. I was saying conference, but it is summer school. And they would like to say a word. They will be always very happy to come here because it remember me some times ago, I was invited by Maxi. It's really a long time ago. And we worked a lot here, and I met all these nice guys, and we worked together. I remember for optical, for parametric optical oscillators and so on. And since that time, we have contact, of course, and we had contact for a long time with Maxi, who visited us for some times also in this period. I am really here for discussing now about what we did this last time. There are some changes in our group, because maybe someone knows that we have a guy who is a really very nice guy, who was one of the first to build really lasers in Lille, and he died, and Pierre Glorieux, then we managed and we changed all groups, and we generate a group with CNRS. And this group was generated in the fact that we can use a tower to build what we call now the photonic crystal fiber. And this photonic crystal fiber makes that we made some project to work mostly on nonlinear fiber optics and the dynamics in fiber optics. This is make the connection with what we... In 2007, there was no activity or rogue waves in optics. And rogue waves, of course, was known for people working in hydrodynamics and so on for a long time ago. But there was not enough experiment. And as you know, in optics, we can do experiment easily and a very short time. And especially for fiber, it's not difficult to do experiment. Then there was a paper, a Nature paper by some guys from United States, and they make the connection between rogue waves in hydrodynamics and rogue waves in fiber. They published a paper. They said, okay, we can make an evidence. We can evidence the rogue waves in fiber, and the idea is that the model in wave surface and the model in fiber is exactly the same, of course, with difference in the coefficients, and this model is nonlinear Schrödinger equation. And this was the depart for this activity of rogue waves, which becomes now very, very hot topics, and there are a lot of things. And there are very in different area of physics, of traffic, and everywhere, people said that they are seeing some rogue waves. And as you know, as there is something which is going well, all people are working this. I get now some papers, and the editors told, is it rogue waves or not? We cannot answer this question. And of course, we have no exact definition of what is rogue waves. There are a lot of different definitions, but the progress is going on. And I think in some years, we can come out to something which is more rigorous about this definition. But we have some signatures. That means that we are in rogue waves. This is what I will show you here. It's a kind of overview what we did this I will show you three systems. One is a Hamiltonian system, which is just a free propagation in a fiber. And two other ones are cavity, which represent a dissipative system. And our idea is, are there any connection to the creation of rogue wave? For rogue wave, are the mechanisms are the same or not? And this make now the connection with a lot of branches in extreme event, also in chaos, in spatiotemporal chaos. And now there is really a very nice and very attractive activity of how to link all these objects in order to better understand what happened in this dynamic. And as you see, there is really a nonlinearity which come out with solitons. Solitons are just a nonlinear solution that can keep their form and propagate without distortions. And rogue waves, chaos, the kind of chaos and turbulence. All these things can be mixed in order to understand what happened. Okay. Then people involved in this work are these are people working in Lille. These are more connected to me. This is a postdoc, and Salia Coulibaly is associate professor who did numerics and theory, and he's really taken an important part in this work. Arnaud Missot and Kudlansky are doing mostly experiment on fibers. And Magno is also doing this, but Eric Louvergnat, maybe you know him, he's working mostly on diffractive system, not in fiber cavity. Mikhail Kolobov is a professor now, hired by the university, and dynamic. I have some work I will show you here from Neil Akhmedev, and it begins with Neil Akhmedev, who was in Lille for 3 months, and this coincides exactly with this period in 2009, and we did some work about how to interpret and how to give some analytical type of log waves. And he sent me some slides that make things very clear. I will show them here. Usama was a guy who did his PhD in Denmark, and he was also in Lille. We generalized the work with Neil Akhmedev. Mustafa Tlidi from ULB, and François Léo from ULB made some experiment on the cavity. Dmitry Scriabin was also in Lille for 2 months, and we worked with him and his co-worker about the cavity. This is the ID globally. Then what log waves in the ocean? I will begin by log waves in the ocean, and then come back to the log waves in optics. Did you see these are some pictures? I take them from the literature. And you can see here, this is from hydrodynamics, and you see that log waves could reach up to 20 feet in high. This is and there was some problems in 2010, and they attribute this to the log waves. And as you see here, these are some problems with ships. This is a picture coming from a Japanese guy who gave these things and thinking to log wave, but at that time we think log wave as something which is more the art than science. This is, as you see here. It's really, you see that this boat is very high, and you see here one which is one of the most important log waves we know here, and this is just to. There are these guys who want to link this picture to true log waves. Okay, then there is the first record of really log wave, because before people think that this is just a near mystical things, and we believe that sailors are drunk, then they said that they saw something on the first time when we record the really log wave. This was this one, we call it the Drompner-Hauer wave. In the circle right, this is this picture here, and this was in this part. And they record one wave which is 20, we cannot see it here, but it's 26 meters high with a period with 12 seconds. This means that really it appears and disappears without a trace, and in 12 seconds, you can completely disappear with your ship. This is really the first time where people become to believe, and I mean scientists become to believe that log wave may exist. And what that means? There are some, in this book you can find the whole details here. There is one of quantitative measure for log waves. We want to separate log waves from waves that we cannot give them the word of log wave. And we defined one significant high, which is 1/3 of the maximum of the whole peaks we have. And with this, we define one abnormality index, which is the high of log waves with respect to high of significant wave. If this is more than 2, we can qualify this abnormality index. Normally, you are always less than 1, than 2, and we have really very difficulty to be more than this one. And now, if you apply this to this, you will find that this is factor 3, which is really more than 2, and this period is very, very small. Then the idea is that log wave doesn't necessitate any flow or nothing. It can really appear from nothing and disappear without a trace. This is the word we give to this thing, and this is coming from From the book I sent you, Pilinevsky and Kharif, they are here. They wrote the book here, this one here, and they classify all what we can call rogue wave with respect to this EI index. And you see here that there are a lot of dead, 30 here, between 1968 and 1994. Then this abnormal index is one of the signature you can have. You can have more than one. And this is not far from here. This is in 2010, out of Hollywood disaster movie, and in northern sea coast of Spain. And this was 2 people killed and injuring 14 of people. Okay, this is really just to situate rogue waves in optic. You can see here that really the publications increase exponentially, and in optics it becomes in 2007. And these are the citations. Okay, now I go to mainly to what I would like to show you. Then if we summarize, we have 2 approaches that we can use in order to study rogue wave. One is deterministic and one is statistic. And the 2 can give some information on the signature of this one. We cannot use only one or the other one. Then statistical approach for rogue wave. First, there is a sensitivity to initial condition. We have never in the ocean a defined condition. Then we have to take into account the fact that initial conditions are completely random. We have also random wave dynamics. And if you use Gaussian statistics, they filled here. If you take the probability to see this, the rogue wave I showed you before, you will find that it may occur in 20 years, which is completely out of order because we don't need 20 years to see this. We see them every 2-3 years. There are one of this rogue wave, which means that the Gaussian statistic doesn't work, and we have to go to something else. Deterministic approach for rogue wave, and then we can rogue waves be predicted? There are some debate, and there are some people that claiming that we can have also rogue wave in linear problem, but I don't believe to this. Then I will not discuss about this, because at last time there are a lot of people who they try to find something on rogue wave, but it's completely out of order for me and for all the majority of people. Then I will not speak about this. They appear from nowhere and disappear without a trace. They have a very high amplitude. And if they appear from nowhere and disappear without a trace, or if they appear, then one only a linear approach can predict the occurrence of the giant wave. And we need, of course, the instability, because from fluctuation, if there is no instability, no growing, then we need an instability which makes that it grow. And of course, we need nonlinearity to compensate for this. In our system, the instability is modulation instability, and nonlinearity is just the dispersion for the fiber. This is the first work we did, a sample model for oceanic rogue wave. As you know, if you have, I didn't make details here, but if you have a fiber in anomalous dispersion, anomalous dispersion means just that you are in the case where I think you can think also to focus in the focus in case. The CW, we inject, you have a fiber, we inject CW, and then we can find that for any CW, it is unstable. It is completely unstable in that case. And this instability is a modulation instability. Then the idea how to convert this modulation instability to a nonlinear object. We do this just, I didn't give it here, but we do this just for nonlinear, pure nonlinear Schrödinger equation. In order to understand, you can see here, this is the CW at the beginning, here. X is the propagation in the fiber. And you see here that the fluctuations that coming out here will grow and reach a maximum, because the problem is nonlinear, and come back to this one. Then you will see something which appear completely and disappear, and coming out for just the fluctuation at the beginning. This solution, it's possible to find it analytically, and this is what we call Archimedes breather, the name to Archimedes, and this is this solution here, just psi equal. Instability, it is on a band, and each wave, from each wave you can generate a nonlinear solution, even more than a nonlinear solution. The most important one, of course, correspond to the most unstable mode. And here you can have them for any, and here you have this parameter that are related to the growth of the perturbation and also to the frequency, the most unstable frequency. Then it's clear that we can construct from a linear instability a nonlinear solution. And this nonlinear solution becomes very interesting because they give what we call now the prototype for rogue waves. And if you go a little bit further, you can see this as a phase space where these are correspond to periodic solution, and if the period, it is found by Peregrine, and it is now known as a Peregrine. If you make now the calculations, you found that there are always these two things and this maximum. All the energy is located on half of time and half of second, of space, which means that there is really a very concentration of the energy at almost one point. And this is make it very, very dangerous. And this is really, now we try to find it experimentally by adjusting the initial condition. And this is the first time in optic we really see Peregrine as a rogue wave equation. Here we wrote this paper, and we call them waves that appear from nowhere and disappear without a trace. And we gave the interpretation of this rogue waves. But there are a lot of paper after there are debate and discussion about if really is rogue waves coming from nothing and disappear completely. And there are these ones and there are these three ones and so on. But it's difficult to see all these solutions. But there are a lot. You can construct them by Darboux transformation. These are the well-known, and they have nothing to do with solitons. They are rational solutions which are localized but not solitonic. And here I give this variety of all solutions, but this picture is very nice because it permits us to understand what happened in nonlinear Schrödinger equation I wrote here. You have this one and this one. These are the first order. And you have this picture here. You can go from soliton, and this point is soliton. This point are CW solution, and at that point there is a Peregrine one. Then you can go from here to here. You will find what we call Kuznetsov-Ma solitons, which is periodic in time, not in space. In the other side, you have Archimedes breather that are periodic in space and not in time. And the maximum here is not periodic in time and not periodic also in space. And you have his of solution if you want. But I will not go in this time. I stopped here with Archimedes. He's doing now a lot of solitons. But I stopped here because we don't see really what happened. But what we do after with Usama is just now we can even manage the rogue waves with some potential. And now with the same formula, we can get all of them. This really was very nice because this solution is completely different one from the other one. And now we have the possibility with this formula in this paper to have all of them. You have just to change this parameter, which is the amplitude of the stationary solution at the beginning. Okay, now I go to inside the problem. We have these solutions, and there are some open problems. One of them, extreme sensitivity to noise and initial condition. I am now speaking about all rogue waves, not only prototype that are the fundamental ones. asymmetric of log waves, non-Gaussian statistic, and need to be beyond the analysis equation. There are also two-dimensional log waves. This is really a very open problem. There is link to extreme event, link to spatiotemporal chaos and turbulence. All these problems are still open. There are a lot of research, but still open. There is no precise and rigorous answer to this. Meaning of predictability, there are some guys who want to predict the occurrence of log waves. There are even commercialization of some kit, and I think it's completely, they can see that log wave is here. I, of course, don't believe of this, and people don't believe too, but on the market you can find. And optical log wave can help also, of course, to understand it, and I will show you why and how. This is now the connection to optics, and as I said to you, this is the first record of oceanic log waves, as you see here. And this is the optical log wave coming from this paper. And you see the similarity is really remarkable similarity of the two. And what is very important here is that we see this in supercontinuum generation in the free propagation fiber. And this is the most important thing for us. This paper was done by launching a pulse in the fiber. And as you know, if I launch a pulse in the fiber, I will end with a pulse because I initiate by something which is localized. The idea is here, is it possible? This was experiment. This was the first experiment. Our idea was, is it possible to generate a log wave as in the ocean from nothing? I mean from nothing, from a calm ocean and just from fluctuations. And we did experiment here, and this is just to show you how this paper has something which is very interesting because they find technically a way to have a gate of time which is very small, not picosecond but very small. Then you can really count the maxima, and this was the idea of writing this paper on the market for fiber optic. This is our experiment. Then the idea here is instead to work in the pulsed regime, we work in CW regime, which means that we can make connection with the calm sea. And is it possible to generate from just fluctuations log wave? And this is what we will call really a wave that appear from nowhere and disappear without a trace. This is our experiment here in Lille. This experiment was possible because we can design photonic crystal fiber at will as we want, and you can have a lot of them with a core which is hollow or a core which is solid and so on. We fabricate one which have some characteristic to generate log wave in it. And the second idea is what is the minimum model that can give log waves. People are using, if you take the paper from Nature, they use 18th dispersion order. You can do nothing analytically. If you have a model with 18 derivatives, then you can do nothing. Our question was, what is really necessary to generate a log wave? What was necessary is just the third order here. This is a pure nonlinear Schrödinger equation. This term, and this is the Kerr medium. This is just the dissipation. Then we take into account the third dispersion and the Raman effect. This one is linear and this one is nonlinear. And these are the main ingredients to generate log waves. Tau by min tau, then this equation will be completely, the symmetry is broken, which is not the case for pure nonlinear Schrödinger equation. And this is the main difference. This is the main importance for nonlinear optics, because nonlinear optics cannot be modeled only by pure nonlinear Schrödinger equation. Then we have a hope with this. This is the experimental result. This is the supercontinuum here, and this is what we get from our model, and the agreement is excellent. Then this is the main result here. This is pure nonlinear Schrodinger equation. And this is signature from nonlinear Schrodinger equation. There is no supercontinuum. The spectrum is triangular, and this stays triangular for all the parameters you have. And if you take now the probability density, you find something which is Gaussian. And there is no log wave because the maximum is coming to 50. Now, if you put just the third order dispersion, this spectrum becomes completely asymmetric and enlarged. And we are not in the beginning, but in the dimension of log waves. This is now, if you see, this is our initial condition, which is around 1 watt. And we come out with something which is around, this is, you have to compare this one with this one, around 1 kilowatt. There is a factor of 1,000 in the peak. And this is really coming from this interaction. When we see now the probability density, you see that there are some, here it stops at 15. These are the maximum of the pulse, and you can get pulses up to 600, which is completely different from one. These are a rare and extreme event coming from here. Now the question is this one are log waves or not? This is what we do after here. Then now we take all of the term, Raman effect and the third order dispersion. And we follow. Here you have the wavelength, and this is the propagation distance. What you see here is the lobes of modulation instability, and you begin to see some solitons coming here from Raman velocity, which is the bigger one. The velocity here is coming from the third order. Then it's proportional to the square of the frequency. And this means that the components have different velocities, group velocities. And the one that have the bigger one will collide with all the other ones and have more and most energy. If now you go a little bit further, this is a picture. We go it from here. You can see this guy is going here, and there is a collision, and after the collision it's going away. This is the spectrum, and this is what we get at the collision. And this is, if you see here, it's around 1,000. And we have these two ones. It reminds the log waves with the two sisters. And this is the really signature of a log wave. Then we can do it now by the probability density. And you see that there is one creation of one log wave. This log wave appear and disappear. These peaks appear and disappear with the propagation. It appears very largely and disappear. And it's not the experiment. If you make this probability density function, you found that it goes very largely for extreme event. That is one of the signatures of log event. This was the first experiment for generating these log waves, but from only from a background without any injection. Some years ago, there are these guys who find that it's interesting to prove what we did. And they said, okay, the third order is important. The asymmetry is important to create these log waves. It's very nice for us, but it's because there was a debate, and they stopped the debate by proving that what we did experimentally and also theoretically, but we didn't go to rigorous theory with demonstration and on and so on. But the debate is stopped now, and it's known that this formation, or this origin of the formation, coming from the fact that there is not a drift but a group velocity, and all these peaks that can be solitons on Archimedes breeder or what you want, abnormally high, 1,000 between this peak and the other one, and it disappeared completely. Now there are a lot of people doing this, and there is a lot of experiment. And these experiments now, they are able to, we didn't order this experiment, but there are people, they chose the initial condition in order to generate one log waves in some places, but without any prediction. This is done only experimentally. Then there are a huge experiment about experimental log wave in optic, and then they have the same signature and so on. Now, the second part is what happened if the system now is dissipative. The problem is completely different. Dissipative system and Hamiltonian system has different dynamics. And here you have not some variant that you can use like a Hamiltonian and so on. And these systems are well known that they can be chaotic, but the chaos is a little bit very small in comparison to the stochasticity of the other one. Then we took now, I will just show you the results. We took now, the cavity is, we took exactly the same parameters. We have always the breaking of the symmetry, and these are the boundary conditions. And if you take all these boundary conditions, this is well known. You can transform this equation. It's well known from 10 years ago and even more. You transform this equation to a kind of generalized Lefebvre equation that Damien knows very well, and Pera also, because they are working also on the same equation. Here we have just this term and these two terms. Now with François Liot, and as you see here, these are some solutions. You can have a train of soliton or only one soliton or stationary solution, but we are not interested with this. This is the experiment in Brussels, and it was difficult to find to break the symmetry here. We overcome this by designing another scheme, which I show you here, where what we tune here is not the third order, but the second order. And it's easy to turn the second order and to compare with the third order dispersion. This is the experiment. As you see here, this is, of course, the pump, and there are stocks, and the stocks are the modulation instability. But you see that these are completely different one from the other, and there is the asymmetry here. This was a challenging problem because people, every time they see this asymmetry in the spectrum, but there is no prediction and no theory for this. This was not an easy problem. We said, okay, we will try to do something about this. This is the experiment, but we changed the dispersion itself. And as you see here, not all the value give rise to the asymmetry. This means that there is an optimum, and the optimum is here. And here, this is the difference between the two peaks, and this difference is very high, which means that you initiate the asymmetry here, and something new are coming in the problem. Then you initiate the asymmetry, and there are group velocity. There are two things, the asymmetry which is coming and the group velocity, and the things becomes more and more rich dynamic. This is the result of our experiment. What you see here is our predictions, is the red line. The blue ones are the experiment, and the red ones coming from the mapping, the original problem, which was not approximated. And you see that there is a peak corresponding to one optimum of this asymmetry. Then we take this optimum, and we would like to see if we will enhance the formation of a log wave. This have been, everything was here. You have all this thing in the paper. There is experiment, the theory, and the relation you can have, and the predictions, and everything goes well about this. Then if you go first time, we find the same thing. Then we find here, from the fact that there is the asymmetry, there is also a convective and absolute instability. And we find that absolute instability, you find one peak, which is normal. But what is interesting here, as soon as we cross the threshold for absolute instability, I am sorry, but I give nothing about absolute and convective instability, because people here worked a lot on convective and absolute instability, and they supposed, maybe I am wrong, that all of you knows about this. If not, you have just to ask Maxi. He knows very well all this thing, and he was one of the first to speak about this. Yeah.
Many people that are not so familiar.
Ah, okay.
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 What is the difference?
Yeah, okay. I will just then give the difference with hand. It's maybe very easy to do it with hand. If you have any instability in a problem with some breaking of symmetry, but let us say that we have just a drift, then you have to compare the growth of instability and the drift amplified. You will completely leave your vision without any amplification. If now the growth win, this means that the wave packet will have time to grow, and then in that case, you will see something growing in situ. The last take is absolute instability because everything is growing in situ. The first one is convective instability because the wave is amplified, but in the same time it propagates. It doesn't have time to be completely amplified to the infinity. Then, which means that the instability will split into two instabilities. One where the propagation win, and another one where the growth will win. But what is interesting here is the consequence of this. The consequence is in the convective instability, if there is any noise will amplify and go away, and amplify and go away, which means that's important. In our case here, it's really very interesting because it gives us some information about the noise we have, because the solutions bear with them the noise they create them. And this is making it more complicated to understand. Okay, then here, when we go to here, I will have completely something new here, because when we cross the absolute unstable point, it completely coincides with the appearance of chaos in the system. We didn't prove it. We are working on it. But for all the numerics, as soon as the absolute threshold is reached, the chaos is in the problem. As you see here, there is a chaos as a burst here. This is the spectrum. You can see that there is something which is not new, and the theory makes it chaotic. Then we go further. This is the spectrum. This is what we put initially, and this spectrum here is triangular as usual. With the breaking of the symmetry, it becomes a little bit large, and you see here, of course, if you take two of them, some peaks are coming here, and the probability density calculations make that there are some heavy tail corresponding to one of the signatures of log waves. And we did a little bit more. We take into account Raman scattering, and you see here that it becomes a huge supercontinuum. It's not easy here. We began with something which is monochromatic, and we came out with a lot of frequencies, which is completely surprising at the beginning, because this means that the non-reality gives you all frequencies from only one frequency. Linear problem can never do this, because the spectrum is preserved. If you put something which is red only, you find the red or nothing if it is dissipated. Here you will find a lot of, and there are a lot, of course, also of application in technology, because we can take that one and we do what we want. We can take that one. This is easy because the fiber, it's easy to do, and you can just go to the end of the fiber and get your spectrum and choose the frequency you want. It's really very important technologically, but it's easy to do. And a lot of medicines, they are contract with us, and they get the spectrum and they do it for anywhere. Okay, then here you see this evolution also. This is Turing instability, and you get here the spectrum. And you see here, these are the two labs for modulation instability, and it's grow really, and you see here really very expanding. We were surprised because for me it was the first time I see a supercontinuum in highly dissipative system. It's not a dissipative system close to Hamiltonian. It's really very high dissipative system. Normally, very high dissipative system, I never see that it's large, so large than this. Then we can get that one, we get even more than this one. Which means that now, if you make This L-shape probability, L-shape is this. This means that there are, you see here, we are about 2,500, and we can get one peak here, which is really very, very large. And this peak, you can find them here. This is the space map solution, and you find that there is always one peak that appear and disappear. Well, there was, for people who was interested, what we call a roadmap on optical rogue wave and extreme event. There are all people that in this book write the same paper. Then I put here Acme fit all, because all means more than 40 people. So then I will, for the 5 minutes, I will go back to space rogue wave now. This is also a cavity, but now the system is not a temporal system, but it's a diffractive system, which means that I am seeing what happened in the transverse direction. And this is the temporal one we discussed about. And here, this is a liquid crystal, and if you shine it, there are one situation where you find something with a lot of fluctuation. And you see the similarity. We're surprised, and we see, okay, maybe we can find them also in this one. Then this is our problem. There is a liquid crystal which we can model as a Kerr medium, and we shine it by a laser, and here you have a mirror. This is a loop. Then you have go and back, and you see what happened at the end of your crystal here. This is a model, really a very simple model, which gives you the index. This is the diffusion, and this is the evolution in time. This is the dissipation, and these are the injected forward and backward field. We try to make only one D dimension. This means that we have a lens which is cylindrical. Then you can transform your spot on only one cigar, and you can use one dimension instead of the two. As usual, this is well-known Turing pattern. And if you increase a little bit, we find something like this. And this is what we got here. If you really see what happened in this cut, you find that there is one very high peak. And we try to, this is the pumping is going this way. At the beginning, you have something which is oscillating. These are Turing instability. There are two peaks. If you go a little bit further, there is the subharmonics coming from the nonlinearities. If you go a little bit further, then you go to something which is continuous, and it becomes completely continuous, which is one of the signature of chaotical situations. Not all, but this is only one. And here we put the probability density of them. And of the first one, there is nothing interesting. And you see that this stealth is coming also. Well, these are our experimental values. And as you see there is a generation of supercontinuum. And with this supercontinuum, there are sometimes these events. This is the probability density for all of them. This is the first one. And here you see that there are some peaks which becomes a little bit more dynamical, complex than that one. And here you see that it's associated to this peak, something which is more tailed here. And we increase, of course, it's not written here, but this is 1 threshold, 2 threshold, 4 threshold, and 9 threshold. Then you find here this very big peak and corresponding to that one. Now the experiment, we do exactly the same thing in the experiment. And in the experiment, we cannot change the intensity as we want. Then we change 3 times here the intensity. These are the Turing pattern. It becomes a little bit complicated because of the nonlinearity. And at each time, we generate one giant peak, which has exactly the same we see in fiber, in propagation in fiber and in the cavity. Which means that the generation of rogue wave is coming mostly from the instability, it can be Turing instability, modulation instability, and from the nonlinearity in the system and the saturation. This is the experiment, and this is numeric, and it's going very well. But if you see what happened now in the space-time, we didn't prove it, but I will give you just a paper at the end where we are doing now. We don't know if at that time, that if there was a spatiotemporal chaos or turbulence. Then we do some calculations, and we answered this now. And as you see here, we calculate this abnormal index, and it's just above the threshold, which is 2.1, which means that we generate log wave, but we are really in the limit of the log wave. And we can increase the intensity. Never we go further than 2.1, which means that this measure is really a very good measure to see if wave have really a very high amplitude or not. And to be more specific, we try to use functions that are known to measure the extreme event. And this is the generalized gamma function. And as you see here, there are 1, 2, and 3 parameters. Then you can write this parameter. If A equal 1, then you can have exponential and so on. Then they give you different functions that can fit your probability density. And this probability density can correspond to extreme event or not. And here we find really that this parameter correspond exactly to what in mathematics they call extreme event for that one. And this is in, I have 2-3 minutes. Yeah. Then I showed you for temporal one, which are the mechanism of formation that was collision of intense wave. I showed you that the convection was very important because all these terms are breaking the time reversal symmetry. And this is really very surprising because all the extended form of nonlinear Schrödinger equation that are used in hydrodynamic, all this term break this reversal symmetry in time. And in the fiber, all terms break the symmetry. I don't know if it's a coincidence or if it's really necessary. I have no answer for this. But all higher terms in nonlinear Schrödinger equation break this time reversal symmetry in time, which means that this moving and this group velocity which is generated in the system, and the fact that all this dynamics can be related to the noise in the system. And this is why we asked to Misha Kolobov, to try to find, we write one paper on this, how we can link this to the quantum fluctuations, because in this system there is always something which is linked to the noise in the system. Then there is maybe a link also to quantum fluctuations. And of course, this is the minimal model for fibers, of course, not for any problem. And in the spatial problems, we can make exactly the same thing. Modulation instability is now Turing instability. And of course, supercontinuum in frequency correspond to supercontinuum in the space frequency. And we find exactly the same characteristics. And we were able to generate spectrum. And we tried to use, to make some technology in similar to what we do in supercontinuum in fiber. But now with space, it's going in now, but I cannot tell you more than this. Thank you very much. I hope that it was not so esoteric for some people, but...
Questions?
questions actually.
Yeah.
So the first one is in the case of can you go back one slide?
Yeah.
So yeah,
Yeah.
great. Yes. So the in the case of the temporal collisions,
Yeah.
so in the collision of intense waves, yeah. So this is a conservative case.
This is a conservative.
So
In our calculation, it's conservative case.
so you put an initial condition
Yeah.
which has some pulses, or you don't, or you
No,
don't.
no. Just what we put is a continuous wave
Okay.
and noise is in the problem,
Okay. So
in the fiber.
some places it focus and it gets these high peaks.
Yeah.
And then on top of that you have the drift
Yeah.
that makes them collide. In that case, a very huge one.
Yeah.
Okay.
Exactly.
Okay. And then since this is conservative, after this peak, what happens to the peak, to a high peak? It just spreads again,
It disappears completely,
and then you get fluctuations, and if
another one come.
and there is some recurrence, or so I mean.
No, there is no recurrence in that case.
So it will form randomly.
Randomly, yeah, exactly.
But
Arno did some calculations, and one experiment with nail, they found that we can have also Fermi-Pasta recurrence in this problem, but with special conditions, initial conditions, and so on. We went really to find it by hand. But if you do things normally, this was the idea here is just to take a calm and CW initial condition and let the noise do its work. Then is it possible to assure that in the ocean we need nothing? Some rogue waves can appear from nowhere. You have a calm sea and you have a very big pulse that appear and disappear from uniform.
You need some fluctuations, so calm, not.
Of course,
No.
in the ocean there are fluctuations.
Some low waves.
Yeah,
Low waves,
some waves, linear waves if you want, but with small amplitude.
Linear waves enough.
Yeah, with the small amplitude. But then the instability is most important. If the system is unstable, then it goes, you know very well this. It gives rise to some amplifications. The instability is absolutely necessary.
Okay, I have more.
The second one. Okay, there is a second one.
You have put emphasis on the dispersion terms, but in the first and the second time you wrote some nonlinear Schrödinger type equation. In one of them there was a time integral on the nonlinear term, and in the other there was no integral. So can you comment, is this necessary or not, the non-local terms in memory or something like that to generate these kind of things?
I have no mind that there is any non-local term.
I think the first time that you wrote some nonlinear
I will
Schrödinger
come
equation.
back to this. The equation I wrote at the beginning.
There.
Here. This one.
So
okay.
is this
Okay.
relevant? Is not relevant?
Yeah. This is the Raman effect. Yeah, I agree with you. Normally it's like this. But in all calculations, we take only the linear part of this one. The linear part doesn't mean that it's not nonlinear. The linear part, it gives this term. The linear part gives this linear Raman term. Yeah, this term here. If you just linearize this integral, you linearize around this tau, then it gives you this derivative, and the remaining term is Dirac function. Then it goes away. But then it gives you this term multiplied by that one, and this is a nonlinear term coming from the linearization of Raman scattering. And this is the usual term for the cavity, which is around 5 femtosecond or something like that. No. The nonlinearity, the nonlinearity is very important, but not the kind of the nonlinearity. What is interesting here, as you see, but we can see it also on the integral equation. This breaks the symmetry tau minus tau. We can see it also from that one. But we need this nonlinearity to go further in generating the rogue waves, the very high rogue wave. We did some calculation by putting this term equal to 0. Then it gives you some It gives some supercontinuum like this one, but it's not a fully supercontinuum. In this, there is no Raman scattering. This is only the third order term. You can compare it to that one. See that the asymmetry is here and it's enlarged in comparison to that one. But it's not sufficient to generate very high log wave. If you add now the other one, you can see if you add now if you add now Raman, this is just without Raman scattering, it becomes very large. As soon as the system enters a nonlinear regime, this term becomes important, as you know.
More questions? I have some questions myself. The first one is the definition of log wave in itself and the concept. I mean, at the very end, when you have log wave, you have a spectrum of the size, which is power law, which means that there is no characteristic size. So then a log wave is none more special to have 2.6 times the background level than to have 3.7 or 10.9, because a spectrum which is power law, there is no characteristic size there. So knowing that, to which point it still makes sense to call log wave something that has 2.6 times. I mean, once you know that, why you keep still that definition? And should that be reconsidered and somehow and put that in another context?
This is a very important question. We have it any time. This is a very important question because we don't know what is really a log wave. You will see if you tape on the computer on internet log wave, you will find a lot of things. We don't know really what is the log wave, but what we know is some signature coming from. Then for me, for the moment, we are comparing to the surface ocean. And in surface ocean, the main things is one, that the signature is this abnormal index. This was really very important for people working in hydrodynamics. And I have the experience, we don't go above this number 2 if really the problem is not. We can increase in our problem, we increase the power, it becomes very high, but the abnormal index never cross the 0.2. This is the first one we use. This is the first signature. The second one is coming from the probability density, that it can give you L shape, which means that there are some extreme events and not as Gaussian.
In logarithmic scale is a power law.
Yeah, exactly. But then a true definition of what is log waves, no one knows what is. This is why a lot of people are now publishing papers where they say we see the log wave, and a lot of people working in temporal dynamics, as soon as they saw one peak coming from crisis, or they say we have a log wave. But why not? People have to let people working and progressing, and maybe in the future we will have.
And another question linking the two topics that you have discussed. In the first case, it is, I mean, you argue that the key ingredient to get this log wave is to have drift, so there is a breaking of the symmetry in the time.
In our case.
In your case.
In the fiber.
In the special case, you don't have that symmetry there. In the last topic that you discussed. Do you
of the space?
The spatial.
No.
There, you don't need that sort of breaking the symmetry.
This is why.
So what is the key? What symmetry do you break to get that, or what is the key ingredient in that case?
Yeah, the difference is here in the second one. We are in dissipative system, and we can increase the injected power. In the fiber, you put your power, and the system will propagate.
Okay, so if you add some dissipation in the fiber, you might not need, for instance, the advection.
Yeah, this is ultimately static in the diffractive system. Okay. But we can increase. This is why we were really it was very difficult for us to find the log wave. We find the log wave in the limit. And after a certain time, we increase the power, but it doesn't we can't go a little bit further because there is no this drift and there is no way to enhance the formation of rock wave. We generated the maximum we can generate. Fortunately for us, we were happy because we just generate rock wave, breaking of the symmetry, and no enhancement of rock wave. But we still see one, which is coming, of course, from this peak, which come from the nonlinear dynamics and from the chaos. Our system was completely chaotic in both cases, but here is chaos in dynamical system.
Okay, thank you. If there is another other question.
Just one word, because maybe we made calculations of this peak when it appears, this peak at the beginning. If we have a rogue wave, no ship in the world you calculate the high with the water and you calculate the pressure on any ship in the world. No one can resist to this pressure. It can go completely inside, which means that I hope for you and me never to be in face of rogue wave, because there is no way for 10 seconds